Great to see you here. We are in the fourth video of the first paragraph. This is the last video of this paragraph. Here we're going to look at set notations with quantifiers, truth sets, and quantifiers. So those are two topics that I will cover in this video. Let's have a look at set notations with quantifiers. We've seen quantifiers before. We look at a statement. For example, we had the universal quantifier for all x elements of S for which p of x is true. So this is in fact an expression using the universal quantifier that signifies that px is true over all the elements x of the set S. Now, when we have another example here, let's have a look what these different elements mean. For example, we have here for all x elements of R, means for all x which are real numbers, x to the square is larger or equal than 0. Basically, here we say that on the set of the real numbers, p of x to the square is larger than 0, which means that the square of all real numbers is always positive. So this is a universal quantifier because this is universally true over all the real numbers. We know that a negative real number, the square of a negative real number, becomes, of course, a positive real number. Now we can also use the existential quantifier, and we can say that there is a value of x, element of the integer, so x is an integer for which x to the square is equal to 1. And this means that there is an integer for which x to the square is equal to 1. And we can find that integer is 1. Since we have an existential quantifier, it is sufficient to find only or at least one example. And that example is very simple. It's for x being equal to 1. And then this is in fact true. So these are set notations where we are using quantifiers, and quantifiers relate to the set of which x is an element of. The next element is about truth sets and quantifiers. What we are going to do now is combine the concepts from the set theory and the predicate logic that we've seen in the first chapter. And we consider a predicate P and a domain D. The truth set of P is the set of elements x in the domain D for which P of x is true. Let's have a look at some predicates and their truth sets in the domain of the integers. And we have here different predicates. The first predicate, P of x, is the absolute value of x is 2. Q of x is x to the square is 2. And R of x is the absolute value of x is x. Now let's have a look at the first one. The absolute value of x is 2. We're in the domain of the integers. So basically we can find here two numbers, -2 and 2, which comply with this condition. And we call this the truth set of P of x in the domain D. Let's have a look of x to the square is 2. Can we find an integer for which x to the square is equal to 2? Well, basically, we have to find the square root of 2, but the square root of 2 is not an integer. We have the square root of 1, which is 1, the square root of 4, the square root of 9, and so on. But in this case, we cannot find any element for which the predicate is true in the domain of the integers. And basically we can say that the truth set in this case is the empty set. And for the last one, we have the absolute value of x is equal to x. Now, what do we have here? We have to remember the definition of the absolute value. The absolute value of x is equal to x when x is positive, and the absolute value of x is equal to minus x when x is negative. Now, absolute value of x is equal to x. This refers immediately that we are looking at the natural numbers expanded with 0, because the absolute value of 0 is equal to 0, or we can also call this the set of the positive integers. So this was the part about truth sets and quantifiers. We are ready now to go to the next paragraph, and there we will be looking at set operations. We will be looking at how can we define operations on sets and with sets. And that's in fact all for this video. Of course, you're doing a great job. You finished another part of the second chapter. I'm looking forward to seeing you in our next video, and thank you and bye-bye.